Thank you for the invitation to QMAT, to Satyabrata and everyone. They have done a great job. I was intrigued by the talk and I forgot I had to give a talk next. I partially forgot my question which I was asking. And it's also I'm coming back to talk about vortices after some time, quite some time. So this is something that we have been doing. The work has essentially been done by my student Saurav Tamogno, and we had a very ongoing and very interesting collaboration with Ravi at ISAR Bhopal. And this is something that I have returned to recently again in high TC superconductors, and that is to look at incommensurate vortex states in high TC superconductors. And these are intrinsic. These are not something that we generate. These are intrinsic. So let me talk a little bit about these commensurate, incommensurate states. So you can take a simple spring type of a system where particles are attached by springs. You can think of them as elastic interactions inside the system, which have a periodicity of, say, let's say 2A0 in them, or A0 is the periodicity of the system, described by this sort of an energy. And then you can bring in a weak periodic potential on the system, and then if this potential is weak enough, this will dominate over the underlying periodic potential, which has an periodicity of B, and there will be no matching between them. It will just float on top of it, and this is the incommensurate state. But then if you tune this interaction strength and you start making it stronger, then you can land up into states where these will try to match with the underlying potential, and they will distort a little and they will try to they will try and match with these, and you can get various sorts of filling, like twice of A0 is filling up 3 of these underlying potentials inside the system, so you get 2/3 filling and so on. And you can also have situations, if you make this potential very strong, then there will be a particle which is sitting inside each of them, so you have the complete filling. So this is the commensurate state. You can have partial states, and if you have a parameter in the system, if you vary this A0 and you have a strong underlying interaction, and if you vary, say, the A0, then you don't have a continuous matching of these particles with the underlying potential, but it can stay in a certain state, let's say 2/3 state, and then it will jump to another sort of a filling, and these are called as devil's staircase. So as you vary the particle spacing, then they will try to match the underlying potential that you have inside the system, but there is no continuous way in which you can go from a commensurate state to an incommensurate state, but it goes through these step-like features, and these are called as devil's staircases. And you can have various sorts of fillings, like fractional filling. For every 2 of these underlying, there is only 1 particle, and then after every 2 you will have another particle, and that is half filling, and then 2/3 filling, and so on. So this is what you have. So what you can do is you can try to distort the system if you have an underlying pinning potential, and the system will and you can also have other interesting physics where the system, if you try to distort it, this is the underlying pinning potential, you try to distort this system and try to fix it or push it inside this pinning potential. So they will form an ordered state, like 1 particle per hole, 1 particle per potential, and then it will sort of, the elastic energy will actually start increasing in this region, and again then it will match with the system, so you have a domain wall formation. So these domain walls are called solitonic excitations inside the system. So you can have commensurate states and commensurate states separated by domain walls. And if you have a lattice of these domain walls, then you actually start entering into the incommensurate state. So you can get from a commensurate to incommensurate state by creating a lattice of solitons, and you can see this physics across various areas of condensed matter physics. Charge density wave is an example where you have the atomic lattice and you have the electronic states, which are actually the electrons which will actually try to form the CDW state. Spin density wave state can be commensurate and incommensurate. Atoms adsorbed on surfaces, moire structures, bilayer graphene, You can have similar sort of features where people have seen actually domain walls between different types of commensurate phases inside the systems, fermions, and finally you can also see it in vortices. So this is what I will talk about, is looking at these commensurate states in vortices. And what are vortices in superconductors? These are microscopic string-like entities inside the superconductor. If you apply a magnetic field to a type 2 superconductor, you will form these string-like entities. These are interacting particles because the current around a vortex interacts with the magnetic field of another vortex, and there is a repulsive interaction. The external field tries to order it and put it together, so there is an interaction between these two vortices. And what is nice is that the interaction between them can be controlled by the magnetic field. This is the density of vortices, which is directly proportional to the magnetic field. So if you change the magnetic field, you can bring the vortices close together, or you can move them far apart. And so you can also play around with the interactions between vortices. And it costs energy to deform or tilt the vortices, so they have elastic energy associated with them. And as I said, the commensurate or incommensurate is related to a competition between elastic energy and the underlying periodic potential that you create inside the system. So this has been there for some time, and people actually introduce superconductors in which you make holes inside the superconductor, a periodic array of holes inside the superconductor, which are this underlying pinning potential. So what you have are vortices in the superconductor, which are like these balls which have springs inside them. There is an elastic interaction, and inside the superconductor, artificially with various techniques, e-beam lithography, focused ion beam milling, irradiation, or whatever, there are various complex processes by which you can introduce these periodic defects inside the superconductor, and these periodic defects will lead to commensurable states where vortices can actually start matching with these holes that you create inside the superconductor. Okay, and these were started from 1996 on or so, and whenever there is a matching of these vortices with the underlying periodic potential in various quantities that you measure of the superconductor, you will see jumps. Okay, you will see these breaks in curvature. This is magnetization versus field. Field, as you know, is a measure of the density of the vortices. So as you're changing the magnetic field, the vortices are coming close to each other, and then they start filling up these holes. And whenever there is a matching of these holes and vortices, you will see these steps in magnetization. And these have various applications from various devices and controlling vortices inside superconductors in controllable ways. So this was very active, and it was an emerging area. And then people actually wanted to see, why are you getting so many what are these sort of multiple steps that you see? You don't see one step, but you see multiple steps happening inside the system. And these multiple steps, people actually image the vortex structure and what they found. So you have a periodic array of holes, and you have vortices which have another period, and actually each of these steps that you see corresponds to fractional filling. For example, there is one vortex per every 4 holes, and at certain magnetic field, and then as you increase the magnetic field, you will have 2 vortices per 4 holes, and so you get sub-fractional filling. And you can keep on increasing it, and you can go from different commensurate states, and you can have various sorts of fractional filling states that are observed in the system. These are some other experiments where people have observed, actually it's not very clear, again a periodic array of holes patterned on a superconductor, and these are vortices, and you clearly see that the number of vortices is much less than the number of holes. So these are fractionally filled vortices, fractional filling. You don't have the same number of vortices as the holes, but these are quite stable. And what people found was that there is also grain boundaries, or what I was telling you about the soliton-like excitations, where the stress is actually built up. So you can have 2 different filling fractions two different fractional fillings which are actually separated by grain boundaries inside the system, and various interesting effects which you can see in these artificially periodically pinned structures. So this has been there for some time. Our group, way in the past, has actually also done work on these patterned structures where we, for example, in BISCO with a focused ion beam, we patterned this periodic array of 350 nanometer sized holes, and we could control the flux, the fractional filling, and we did imaging on the vortex configuration inside these patterned regions where there is fractional filling, and we could see interesting geometries of flux distributions that are present inside at these fractional fillings. And there are multiple fractional fillings that are actually present. It's not only one fractional filling, but multiple fractional fillings which can be present, and we could control the flux structures. Mainly from application points of view, we were also looking at it, how to control the local flux distribution inside microscopic regions inside the superconductor. So this was way back in the past. Okay, so what is new? Okay, so as I said, that this commensurate incommensurate physics is really related to competition between interactions inside the system, elastic interactions, and there is a periodic sort of a potential that you create by patterning the superconductor, and you can get a matching of these vortices with the underlying, and you can create different types of vortex states inside the superconductor. Okay, and if you go historically, then 1995 you had these artificial antidotes which were developed. In 2000 there were direct imaging, and you could see fractional states which are generated inside. For every few dots there is one vortex or two vortices and so on. And then in recent times, in these artificial arrays, people have also started generating Kitaev type frustrated states, and there are complex flux geometries which are being seen in these artificial structures. What we want to do is that instead of going to such complex complex fabrication processes which involve e-beam lithography, FIB, are there ways to generate such sort of periodic fractional filled structures intrinsically? Okay, and that has been what we want to do, is that is artificial complex patterning processes really necessary, or is it possible to generate periodic pinning potentials inside superconductors, control flux geometries inside superconductors, and generate various sorts of interesting features by intrinsically looking at some intrinsic system? Okay, so that is going to be our goal. Okay, and the strategy that we use is to grow a specific phase of BISCO, which is bismuth strontium calcium copper oxide. Okay, it occurs in two different phases, 2212 and 2223. We looked at the complicated phase. Lot of work has happened in 2212. We were not so interested in looking at 2212 for various reasons. We actually came to looking at and trying to grow 2223, which is a more difficult phase to grow. And we started our work on growing BISCO, and this BISCO that I write as crystal X is your 2223. Okay, this is, and then we will look at some results on this single crystals of high quality single crystals of BISCO 2223, and then we subject also these crystals to different sort of annealing procedures with oxygen annealing or temperatures in certain specific recipes, and we will see what happens to the flux distribution inside these systems. And it turns out that this becomes a nice handle to actually control the flux distribution inside the superconductor. Okay, so we grew this 2212, 2223 phase, and so I will talk about two different sets of samples. One is the sample X. We would grew multiple samples, okay, sample X and sample Y. Sample X is the pure 2223 phase, or mostly the 2223 phase, and the sample Y is the oxygen annealed sample. Okay, this is the Laue pattern. You can see nice diffraction spots of the crystal. Okay, the crystal is very well formed. Okay, but if you do high resolution transmission electron microscopy of the sample X, what you find is that these, you can see the atomic spots. I'm not sure if you can see, these are the atoms of BISCO 2223, but over and above the atoms of BISCO 2223, you see this modulation that you see in the atomic distribution. There you see a periodic modulation in the atomic distribution inside 2223, and this period is about 28 nanometers. Okay, this was very surprising to us. Okay, and this is further confirmed that if you take a selected area diffraction pattern, basically you look at the Fourier transform, but by shining electrons on the system, and then you look at the SADP, selected area diffraction pattern, then apart from the actual Bragg spots which come from the crystalline structure, you will see satellite peaks. You know, for each spot is actually surrounded by 3 other spots, which comes because of the higher Q or the different Q that is associated with the second periodicity, which is this modulation that is present inside the crystal. Okay, and these are in these samples of X. Okay, and if you look at the full width at half maxima, they are pretty sharp. Of these satellite peaks, these are pretty sharp. We see them all over the crystal over large distances. Okay, and so for example, if you take a line cut, each of these modulations is actually picking up an atom in this system, and this overall modulation that you see is this periodicity that you see in the contrast. So there is an inherent 28 nanometers periodicity that is there in the crystal. Now if you do oxygen annealing in the system, then under certain specific conditions, then this periodicity you see is significantly destroyed. It's almost gone. Okay, and you can make out faint sort of periodic structures, but it's a highly quasi-periodic structure. This modulation from 28 nanometers has come down to 14 nanometers, and it is not uniformly present all over the crystal. You can see the spots have become much more, the 3 type of spots that each diffraction which was surrounded by the other diffraction spots has now almost gone in most places. It's present in some places, and it is also the full width at half maxima of these spots is pretty big, which means that it does not have very high long range order. These modulations are not present over a very large distance inside the system. So we could actually measure these modulations. So you have a crystal which is this crystal X, which is the 2223 phase, which shows that inside the crystal structure there is a modulation which is present, and if you do annealing in the same crystal, you can destroy this intrinsic modulation inside the crystal. Okay, and of course there is more data. Now it turns out that people had seen earlier also similar sort of modulations in 2212, BISCO 2212 phase, and this modulation is intrinsic to high temperature superconductors like BISCO, because you have this bismuth oxide, strontium oxide, rock salt like structure which sits on a perovskite structure. There is strain in the system, and this strain which is there inside the system leads to this sort of a periodic modulation. But this periodic modulation which people have seen in 2212 and reported in 2008 and also till 2019, people are still looking at it, is on the length scale of the order of few 20 nanometers or so. We see something which is like 26, 27 or 28 nanometers range, which is there inside the crystal. Now it turns out that 2223 phase diagram, whenever you try to grow 2223, little bit of 2212, the 2212 is the most stable phase, and that always tries to grow when you grow 2223. And when you grow 2212, a little bit of, or when you try to grow 2223 phase, a little bit of 2212 always enters inside the system, and there is a 1:3 ratio. And if you do a simple sort of a structural analysis of 2223 and 2212, and if you take one unit cell of 2223 and 3 unit cells of 2212, you will be able to see that there are these modulations because the heights of the cells are not equal, and you will see a modulation which will emerge, and this modulation, order of this modulation is around 28 nanometers or so. So whatever be the mechanism, okay, it could be intrinsic strain which is definitely present, but also there is this feature which has been missed often, is that you can have a little bit of 2212 and 2223 both present inside the system, but the most important aspect is that intrinsically inside the crystal you have a modulation in the crystalline structure, in the order inside the crystalline structure. Now, does it lead to anything more than that, or it's just a modulation inside the crystal? Or does it couple to the vortex state in some way? These are superconductors with transition temperatures of around 100 Kelvin or so. Does it lead to anything significant on the vortex state? Because crystalline modulations needn't couple with because you need to generate pinning inside the system. Okay, so now this is these single crystals that we have grown. This is their magnetization. So this is the crystal X that you are seeing here. This is at 10 Kelvin, a magnetization versus field, and what you see is that there are these peaks which I had shown you earlier in the superconductors in which you had drilled holes inside it, the artificially pinned superconductors where you had created a periodic pattern of holes. These are superconductors in which there is no such artificial patterning, but there are these intrinsic modulations which are there, okay, which you can see is whenever the vortex state matches with some pinning inside the system which is periodic, you will get a step in magnetization, and these magnetization steps occur at very fixed sort of magnetic field values. Okay, these are the magnetic field values that you can pick up very regularly. Okay, if you go to the sample Y, from sample X, if you go to sample Y which doesn't have these periodic modulations, you see that it is smooth. It is almost smooth. You don't get these periodic modulations, and as you increase the temperature, you will slowly make these steps disappear. Okay. If you measure the critical current of the superconductor, you can see these modulations very clearly. Okay. And these again correspond to fractional, these also correspond to commensurate states which are being generated inside the superconductor. Okay, so it looks like this crystalline modulation that is present inside the superconductor is actually causing periodic pinning potentials within the crystal, and they are actually catching periodic commensurate states which are being generated inside the superconductor. Okay. And if you go to sample Y, of course it's clean and so on, and I'll not say more about that. But then you can do something called as a pinning force analysis. I'll sort of skip the details, but what we want to show is that if you capture the pinning force which these vortices are experiencing inside the crystal, then you can do some sort of a fitting, and this fitting actually tells you that the nature of the fit actually tells you that these the type of pinning that is present inside the crystal is not coming from TC variations inside the sample, but rather they are coming from fluctuations in the mean free path of the electrons which are there inside the crystal. Okay, so the modulations, and over and above this delta L pinning, it's called as delta L pinning mechanism. Over and above the delta L pinning mechanism, you see these fluctuations which are corresponding to the commensurate state. So it looks like the modulations in the crystal are periodically modulating the electronic landscape inside the superconductor, and these variations are actually coupling and varying the vortex core energy to give rise to periodic pinning inside the crystal. Okay, people in the past in BI2212 actually have looked at, with STM, they have looked at the gap, and the superconducting gap also has shown periodic modulations in the superconducting gap, where the period of the superconducting gap, wherever I had shown you those crystalline structure modulations, they occur at the same Q as the crystalline modulations. So not only is the electronic mean free path modulating, but also the gap is modulating. We believe both of them may be happening, and both of them, because the vortex core has both contributions which are coming from the variations in the mean free path as well as the condensation energy which can vary. Okay, and both of these I think are participating and playing an important role to create these intrinsic modulated states and cause pinning inside the crystal. Okay, so we looked at various sorts of methods to actually analyze the data. I'll finish quickly. Okay, And this is a summary of the vortex state that is generated with this commensurate. So this is sample X. You can see that this phase diagram, this line is the line above which thermal fluctuations dominate inside the crystal and they destroy any sort of pinning inside the sample. This entire region below this line is the vortex solid phase, and these black lines are where you can see these intrinsic commensurate states which are being generated inside the crystal. These intrinsic commensurate states are populating the vortex solid phase, but they don't enter into the fluctuation regime which is above this line. As you go to the sample Y, which is the one where you have thermally annealed the system, all these modulations are gone and it has become more or less a different sort of a, it's a sort of a, not a periodic sort of a pinning potential, but it has sort of become more closer to random pinning inside the sample, and these sort of features are removed. So clearly the intrinsic structural modulation gives rise to, it couples with the electronic states and is giving rise to periodic pinning inside the sample. We did a sort of, and if you look at these values and if you do an analysis, then they correspond to a hierarchy of fractional filling. Each of these steps actually corresponds to 1 by 9, 1 by 15, 1 by 18, 1 by 20. So, you know, you can have a hierarchy of filling fractions which are actually populating the intrinsic pinning landscape, periodic pinning landscape inside the system. And we have a simplistic model where we have done a Monte Carlo type of model where you have a periodic pinning inside the crystal, and then we put in vortices inside the system, and these vortices are thrown inside the system, and you can vary the periodicity of these periodic pins that you generate inside the system. And if you look at the energy cost of putting a vortex inside the crystal as a function of the filling fraction, how many periodic pins are filled by vortices, then you will see that there are these kinks that you find in this change in energy, and these kinks that you find in change in energy are occurring at fractions of 1 by 8, 1 by 4, 1/2, and so there is a full hierarchy of filling fractions, and these filling fractions can change as you go, as you change the periodicity of the periodic pins inside the crystal. So we have established that there is a hierarchy of correlated pins that you can generate in these intrinsic superconductors, high TC superconductors, provided you can generate this periodic sort of a potential inside the system, and these are pretty important. We are going on to imaging, and we are going on to various sort of interesting structures that we have planned for these, but this is, I'm sort of running out of time. There are interesting domain structures also that we believe exist in these systems, more later for that, but I just forgot to mention that many of these systems, as you go from 1 by 8, for example, P is equal to 3 is this green curve. These are the periodic pinning centers, and the red spots are the vortices. So you can see there is one vortex per few pinning sites, and then you can fill up few of these pinning sites, and then as you increase the filling fraction, then you can have vortices which are present in between the pinning sites, and it turns out that these are called as interstitial vortices. These interstitial vortices are very important for stabilizing the intermediate interactions, turn out to be important for stabilizing this filling fraction. So finally, it looks like structural complexity itself emerges as a design parameter for some of these collective quantum states. This is something that we want to progress further on and come up with more interesting devices structures. And so I'll stop here. This is the summary, that we see a hierarchy of commensurate states in intrinsically superconductor, and we don't need artificial patterning techniques.
Okay, thank you, Satyajit, for a wonderful talk. The session is open for a few questions. Yes, please.
So how do you deterministically control, engineer these?
Actually, we didn't. We cannot. So what we did was we just grew 2223, and then when we started looking at the XRD peaks, that's the first time that we realize that there is a 3:1 ratio of 2 to 1 to, most people don't look at it so carefully, but you can see a satellite which is developing. Then when we looked at it more deeply, we saw there is this admixture of 2212 and 2223, which is, but this does not happen in 2212 if you grow. That's the one which is the most stable in the phase diagram. You know, 2212 grows very nicely. 2223, if you try to grow, it's very difficult to get a pure 100% 2223 phase.
So so do you think it's because of some growth conditions that you can do?
It's possible. We have not reached the sweet spot where you can grow 100% 2223. But the fact remains that even if you grew pure 2223, the rock salt structure of BiO, SRO and the perovskite structure of copper oxide, calcium copper oxide, they always have a misfit. And that always gives rise to an intrinsic modulation in, so there is an intrinsic periodic modulation which people show couples to the electronic state, you know, the gap, and now that we see even there is a delta L pinning modulation that is there in the system.
So thank you very much. I'm not from this field, but I have a simple experimental understanding problem. So if I understand correctly, if I have a homogeneous sample, right? So then you apply the external magnetic field, and then basically you get a kind of vortices. Yeah?
Yes.
So this is the very simple thing. Yeah. Now you wanted to go some kind of, that means this is a kind of commensurate or homogeneous things you are getting.
No, there is no commensurate.
Okay.
It's incommensurate because it's incommensurate with respect to the lattice structure.
Yeah.
You will talk of commensurate or incommensurate if there is a second period present inside the system. Okay,
Yeah.
so now one you have is the periodicity of the vortices, and the other is the periodicity of, let's say, the atoms inside. For example, niobium, if you take, the niobium has some periodicity and the vortices have some periodicity. So the vortices could be completely incommensurate with respect to the niobium atom periodicity inside. Okay, but here we are generating long wavelength modulations which have a certain period, and the vortices go and start match with that underlying modulation period. That
Yeah, so, okay, the first part I completely didn't understand. Now I understand
Okay,
this part.
okay.
But the second part, that means these follow-up things are coming up.
Yeah.
Now, basically, we are not really sure about the sample homogeneity now, right?
No, it's not that it is not homogeneous. It is homogeneous in the sense that you could have 2212, okay, which is pure homogeneous, but still there is intrinsic modulation because intrinsically there is a strain inside the crystal where there are these modulations that you see. Here, along with that modulation, we believe there is a repeating structure of 2212 and 2223 which is present inside the system. So you might want to call it inhomogeneous. For us, it is just that it creates, it's something that is present not locally. Inhomogeneous is something which is present randomly. If it is present randomly, we wouldn't be seeing this sort of a commensurate effect. The commensurate effect only comes if you have a periodic continuous modulation which is present inside the system. That's why I showed you sample Y, that when you sort of do annealing in a particular way, you lose the commensurability effect completely, because then it becomes random distribution of these modulations are only present in local spots of the sample, and you can see that there are no commensurable features. Okay.
Hello, sir. So basically, here you are changing the annealing parameter, like at what temperature.
For Y, for sample Y. Yeah.
So then you get the periodic pinning potential, right?
No, not for sample X. For sample X, these are as grown crystals, but of course they are grown in a particular condition.
And those periodicity, is it reproducible?
Absolutely, we have multiple cases. I didn't show you, but it's long. I mean, you can see it over multiple crystals from all the batches that we have grown, and you can see it across the sample at different places of the sample for sample X.
And also one more question: if we change the periodicity of the
And second,
pinning
I will tell you that the vortex state is not generated locally, it is generated all over. So if it was something which is present locally, you wouldn't see these periodic modulations in the pinning which will appear. This periodic modulation will appear only if this underlying periodic pinning potential is present all over the system.
Okay, one more last question. If we change the periodicity of the pinning potential, then in the M versus H plot, where we get the jumps at a particular field,
They will shift.
they will shift, right?
They will shift.
Okay.
Yeah.
Okay.
Okay, for the sake of time, can we move to the next talk, leaving any further questions for the discussion?